So let's start the final session of the conference. And so Tengren will give the second part of his talk about cusped Hitchin representation.
Okay, so let me just recall some things that we did last time. So remember the first thing we did was we defined this notion of a theta transverse group, right? So remember what that means is that there is a representation rho from gamma to SLDR, right? For which there exists a continuous rho equivariant map C from the limit set of gamma to F theta that is transverse, meaning that if you take any distinct pair of points in the limit set, the corresponding flex that you get should be transversed. And it satisfies this property that I call strongly dynamics preserving, right? So if you take any pair of points x, y in the theta limits in the limit set of gamma, and you have a sequence gamma I in the group gamma, such that gamma I O converges to x and gamma I inverse O converges to y for some or equivalently any O in H2, then rho gamma I F has to converge to Cx for F in F theta that's transverse to Cy. Okay, so this is a theta transverse group. And then we define the notion of a continuously positive and a cusped Hitchin representation as well. So a representation rho from gamma to SLDR is continuously positive if there is a continuous positive rho equivariant map C from lambda gamma to F delta R. Okay, so F delta RD. Okay, so the only difference, so both of these, here you have continuous rho equivariant, here again you have continuous rho equivariant. It's just that here I have positivity, but here I have this strongly dynamics preserving property. Okay, here for me to make sense of positivity, my flag manifold needs to be F delta. Okay, here I can take any F theta. Okay. And then the proposition that we discussed last time is that if you have a continuously positive representation rho from gamma to SLDR, then it is delta transverse and irreducible. And if you take a parabolic element in gamma, then its image under rho or negative of its image under rho has to be unipotent with a single Jordan block. Okay, so this is what we discussed last time. Let me just note that in this entire discussion, my gamma doesn't need to be finitely generated. It's just any discrete infinite subgroup of PSL2. Okay. Then the last thing we stopped, where we stopped was oops, how do I do this? Okay, yeah. We stopped with this definition of what is a cusped Anosov representation. Okay. So let me remind you that so here, in order to make this definition, I need to assume that my gamma is a geometrically finite Fuchsian group, meaning finitely generated non-elementary Fuchsian group. Okay, and then so when you have this group gamma, we can construct this bundle U hat gamma. Okay, which has this flow space U hat gamma. So this is a space with some flow, some R action, and then using so you can do this. You can build this flow space just from the group. And then once you have the additional information of representation, you can build this bundle, right? This vector bundle E rho over the flow space. And then with the additional data of a continuous rho equivariant transverse map C, you get a splitting of this vector bundle into two sub-bundles, one of them rank K, one of them rank D minus K, right? So this was also what we discussed last time. Okay, and so what does it mean for your representation to be K cusped Anosov? It means that you have such a rho equivariant transverse map, continuous, okay? And this splitting here is an Anosov splitting, right? Meaning that you have uniform constants, big C at least 1 and little c at least 0, so that for any positive time, for any vector V in the base, okay, and for any vector Y and Z in the fibers of these sub-bundles, theta hat and C D minus theta hat and C hat over V, when you take these two vectors and you flow them, right, and you look at how the norm is changing, the ratio of the norms, it has to be contracting exponentially, okay? Uniformly with respect to these two constants, big C and little c. Okay, and then we say that, okay, so this is what we mean by a cusped K Anosov representation. Okay, then given theta, if you want to say what's a cusped theta Anosov representation with respect to the norm, the chosen norm, then this means that it is cusped K Anosov with respect to the norm for every K in theta. And then you say that the representing rho is cusped theta Anosov if it's cusped theta Anosov with respect to some continuous norm. Okay, so I need to make the last definition if I want my definition to be independent of a choice of a norm. Okay. So a few remarks. So first, in the case when gamma in PSL2 is convex co-compact, meaning that this flow space U hat gamma is compact, okay, then then oops, this is not U gamma. This should be rho. Okay, then the representation rho is cos theta and north with respect to some norm, if and only if it's cos theta north with respect to any norm, right? Because in the case when my base is compact, when the base here is compact, then any two continuous norms on the fibers of E rho head are bi-Lipschitz. So when you change your norm, that will cause these constants to change, but the existence of these uniform constants do not depend on the norm. Okay, but now my U hat gamma is not compact. Okay, so you can find norms that are not bi-Lipschitz to each other. Okay, and this is potentially a problem. Okay, but one of the punchlines that I hope I get to is to show you, is to tell you that this is actually not an issue. Okay. So another thing that I should mention is in so far here my definition, I take gamma to be a geometrically finite function group, but recently there's the vast generalization of this notion to the case where you take gamma to be any relatively hyperbolic group. Okay, and the theory that I'm going to explain later, there's some analog of that in this more general setting. So that was proven by Zhu and Zimmer. Okay. Okay, so that was what we talked about last time. Any questions before we move on? Okay, so my plan today is I'm going to state some theorems first. Okay, maybe not yet. So, okay, maybe not yet. Let's talk about some first properties of these Carson-Nosson representations. Okay, so I call this the cost geometry of these Carson-Nosson representations. So this is a proposition. Again, I let rho from gamma to SLDR be a cos theta Nosson representation. So my gamma, remember, here has to be geometrically finite. Okay. So the first thing you can say is that for any point O in H2, there exists uniform constants be A at least 1 and little a at least 0, such that if little gamma is in gamma and k is in theta, then the logarithm of the ratio of the k to k plus 1 singular value of rho gamma, right, has to be up to this uniform additive and multiplicative constants equals to how far gamma translates my base point. Okay, so again here, this doesn't depend on the base point. If you change your base point, these constants might change, but the existence of these uniform constants do not depend on the choice of base points. Okay, so right, so why is this true, right? So okay, so basically there are two main ingredients you need to prove this. Okay, the first one is at this point in a Nosson representation, is a pretty standard argument. So what you do is you take a group element whose flow line passes through a ball of radius d centered at my point O. So I fix my point O in HD. I pick a big ball of radius, of some radius, big enough so that it translates cover the entire space. No, sorry. Okay, no, I just need to pick right. So I mean, okay, let me think out. Okay, so I pick my point O in H2. I pick a big ball so that every axis, right, of every axis of every group element, right? Every group element has some conjugate whose axis passes through this big ball. Okay. And then for those guys, right, you use the fact that the contraction, right, of your bundle along that flow line. You can use that to convert it into an inequality that looks like that, into something about singular values. Okay, so this is this is an argument that allows you to convert contraction of the bundle along a particular flow line, right, into growth of singular values. Okay, then you have to use this theorem of Abel's Margulis-Seuffer that allows you to basically once you do that, it allows you to get this kind of estimate for all the possible group elements. Okay, so what that theorem says is that given your group, you can always find some finite set of group elements, S, so that if you take any other element gamma in your group, okay, by multiplying gamma with one of the elements in my finite set, I can ensure that the product of these two elements has an axis that passes through a ball of radius d centered at my base point. Okay. And then, so once you do that, you can get an inequality like that. Okay, so this is, okay, there's some work you need to do, but not super difficult. And if you're familiar with these Nosson representations, this is sort of a standard argument at this point. Okay. Okay, then once you know this growth of the singular values, you can convert that into the growth of eigenvalues as well. Okay, because here you just use the property that the kth eigenvalue of rho gamma is the limit of the nth root of the k singular value of rho gamma to the n. Okay, so that's that will give you this. Okay, so this is telling you that I forgot the log. So the log of the ratio of the eigenvalues. Oh no, sorry, I don't need a log here because I took exponential here. Okay, so the ratio of these eigenvalues grows exponentially with the length, the L gamma. So L gamma is the translation length of gamma in H2. Okay. And then finally, this last one is about the symmetric space. So given my Lie group SLDR, okay, there's a Riemannian symmetric space associated to it. Okay, so this is the analog. You should think of this M as the analog of H2 to PSL2R. Okay, so when my Lie group is PSL2R, the symmetric space is H2. But for general Lie group SLDR, you have analogous Riemannian symmetric space M. So this is a non-positively curved Riemannian metric space that's simply connected. Okay, so now and you have a transitive SLDR action on it as well. Okay, so now if you pick any point O in H2 and any point O prime in M, then you can look at the orbit map from gamma O. So this is the orbit of O inside of H2 to the symmetric space where you just send gamma dot O to rho gamma dot O prime. Okay, and this orbit map here is a quasi-isometric embedding. Okay, meaning that you can find uniform constants big A and little a, so that up to this uniform multiplicative and additive constants, how much rho gamma translates the base point in M is the same as how much gamma translates the base point in H2. Okay. So another way to say this is coarsely. Okay, if you don't look too closely up to this, so that's up to this multiplicative and additive constants, right? How far gamma translates the base point in M is the same as how far gamma translates the base point in H2. Okay, and this here follows from 1 as well. Basically, because you can write a formula for how far rho gamma translates the base point in M in terms of the singular values. Okay, so that allows you to get something like this as well. Okay, so these are first properties of this cusped Nosov representations. Okay, so so here I can state the main results. So the first main result we prove is that, again, I'm in a situation where gamma is a geometrically finite function group. Then the representation of rho from gamma to SLDR is theta transverse if and only if it is cusp theta and Nosov. Okay, meaning that, so in both theta transverse and cusp theta and Nosov, I need to have a continuous r-equivariant transverse map. Okay, the theta transverse condition is, on top of that, your map has to be strongly dynamics preserving. But the cusp theta and Nosov condition is saying that on top of that, your map has to have this, you look at these bundles, have to have the correct contraction. Okay, and I'm saying that those two conditions are actually the same. Having this strongly dynamics preserving property and having this contraction is the same. Okay, so that's the first theorem. Okay, and so as a consequence of this, you can deduce that cusp Hitchin representations are cusp theta delta and Nosov, right? Because I told you that these cusp Hitchin representations are all delta transverse. And so if you know that delta transverse is the same as cusp delta and Nosov, then you have this. Okay. Okay, and then along the same line, so that we prove this other theorem, okay, which says the following. So I start with a cusp theta Nosov representation rho naught from gamma to SLDR. Okay, and then I'm looking at the space which I call Hom TP rho naught. So these are all the representations from gamma to SLDR with the property that this representation rho has to send parabolic elements to conjugates of where rho naught sends the parabolic element. Okay, so this is type preserving on the cusps. Okay. Okay, then the claim is that there is an open neighborhood O inside of Hom TP rho naught of this representation rho naught with the following properties. Okay, so first, every representation in O is also cusp theta and Nosov. So this is saying that this cusp theta and Nosov property is an open condition inside of this space here. Okay. Second, okay, so there is some alpha larger than 0 such that for every row in this open set, the theta limit set 0, right, of rho is alpha Herder. Okay, so not just that all of these, so in particular, cusp and Nosov representations have Herder continuous maps, limit maps. Okay, but not just that, right? I can ensure that the Herder constant is uniform over a small open neighborhood about every representation. Okay. And then third, if you have so if rho u here is a real analytic family of representations in this open set, okay, and I pick any point z in the limit set of gamma, then the map from this real analytic manifold that parametrizes my real analytic family to f theta rd given by u to c rho u z is real analytic. Okay, so what am I doing here, right? So in my open set, I take maybe a path of a real analytic path of representations. I pick a point z in my limit set. So as I vary along my path, right, my limit maps are varying. So you look at C rho z, that's varying inside the flag manifold, and that variation is to real analytic as well. Okay, so this kind of kind of regularity results, right, of the behavior of the limit map, right? This is well known for in the situation where gamma is convex co-compact, when my flow space is compact. Okay, and so we can say the same kind of things in the situation where as long as your gamma is geometrically finite. Okay, so this kind of results, I guess my collaborator Dick Canary was interested in this because he used this kind of results to study the pressure metric on this space of cast Hitchin representations. Okay, but this Herder continuous especially is quite useful because you can do basically what Francis Bonahon and Guillaume Dreyer did to. So at least in the situation where you are cast Hitchin, right? This allows you to define the slithering map, right? And then you can try to do the kind of parametrization that they did in this situation. So I don't know whether I think it should go through, but I don't know. This is a project. I guess it's a potential project for somebody to try. Okay. Okay. So that's that. So these are okay. So my main goal later. Okay, I still have a few more theorems that I want to tell you about, but the main goal later that I want to do is I want to try to at least sketch the proof of this theorem for you. Okay. Okay, so once you know that your okay, so another thing that being a transverse representation or cast a Nossel representation allows you to do is allows you to define certain kinds of invariants you can associate to your representation. Okay, so the first invariant is this thing called the kth critical exponent. Okay, so here I start with a Fuchsian group gamma, and rho from gamma to SLDR is theta transverse. So here I don't need any geometric finiteness assumption. Okay, then for each k in theta, I can define this thing called the kth critical exponent of rho. Okay, so I denote this by delta rho k. And what is this? So what you do is you look at, you fix a number t, and you look at all the group elements, little gamma and big gamma, so that the logarithm of the ratio of the kth to k plus one singular value of rho gamma is less than t. Okay, so the theta transverse assumption tells you that this is a finite set. Okay, so you can take the log of the size of this set, right, and divide by t and take the lim sup as t goes to infinity. So what I'm doing here is I'm looking at the exponential growth rate of the size of this set. Okay, so if you just assume theta transverse, this number can be 0, can be infinity. Okay, it's just some yeah. Okay, but the point is that the theta transverse assumption tells you that these sets are finite at least. Okay, so you can try to talk about the exponential growth rate. Okay, so on the other hand, if you have a geometrically finite Fuchsian group, okay, then you can look at gamma hype, the conjugacy classes of hyperbolic elements in gamma. Okay. Okay, and then if you look at if you have a cast theta Nossel representation rho from gamma to SLDR, then for any k in theta, you can define this other invariant called the kth topological entropy of rho. Okay, so what you do now is instead of looking at group elements, you look at conjugacy classes of hyperbolic elements. Okay, and then you look at the logarithm of the ratio of the kth to kth plus one eigenvalue of rho gamma. Okay, and you count the number of conjugacy classes where this is less than t. Okay, and then again, you take the exponential growth rate of the size of this set as t goes to infinity. Okay, and so now I need this cast theta Nossel condition to ensure that this set is finite. Again, okay, so this set is not finite if you don't know your gamma is geometrically finite. So for example, you can imagine you can have like a function representation with infinitely many pairs of pens, where you make the pens curve shorter and shorter and shorter, then you fix T, you can have infinitely many conjugacy classes less than T. Okay, so I need to stop that kind of thing from happening. Okay, so I have this condition. I need this Nosov condition. Okay, so let me just mention that this delta rho k, right? This is just another way to say that this guy here is the critical exponent of the following Poincare series. Okay, so this Poincare series is a sum over your group of things of the form e to the minus s times log of this guy. Okay, so what does it mean to be a critical exponent? It means that if s is strictly larger than delta rho k, then this infinite sum will converge. If s is strictly less than delta rho k, it will diverge. And if s is equal to delta rho k, I don't know. It might converge, might diverge, depending on what gamma is. Okay, so this is the critical exponent. Okay, and this point of view is actually more useful than this definition when we're actually proving the theorem that I'm going to state next. Okay. Second, this H rho k, this topological entropy, is called a topological entropy because it is actually a topological entropy of a certain dynamical system. Okay, so if you look at the flow on U hat gamma, so it should be hat, not U gamma. Okay, there is a way you can reparameterize this geodesic flow, okay, to ensure that the periods of this geodesic flow are these numbers. Right? And as a consequence of that, this guy will be the topological entropy of that reparameterized flow. Okay, so typically I think of this delta rho k as sort of a more geometric quantity, and this H rho k as a more dynamical quantity. Okay. Any questions about these so far? Strictly bigger than 0, yes. So here, remember when I say geometrically finite, I assume non-elementary. Okay. Any other questions? Okay, so here's the theorem. Okay, so let rho from gamma to SLDR be a cusp Hitchin representation. Okay, and so we know that these guys are all cusp delta and Nosov. So I can define the topological entropy, I can define the critical exponent for both for these representations. Okay, and I pick any k in delta, right? Then the theorem says that the kth topological entropy of rho has to be equal to the kth critical exponent of rho. And this is at least 1, at most 1. Okay? And furthermore, I can say exactly when equality holds. The equality will hold if and only if the group gamma that I chose is a lattice. So that means the limit set has to be the entire boundary of H2. Okay? So in the case when gamma is a closed surface group, this result was already known by Potrie-Sambarino. But in that case, you don't have, in that case, closed surface groups are all lattices, right? So their statement of theorem is that when gamma is a closed surface group, then for any k in delta, the k topological entropy of rho is 1 for all Hitchin representatives rho from gamma to SLDR. Also, in the case, in their proof, they don't actually need to go through the critical exponent. So they don't mention the critical exponent at all. Their proof is a purely dynamical proof. Okay? So let me just say a few words about the proof of this theorem, because here in this situation, we are working with a non-compact flow space. Okay, so we actually cannot use the kind of techniques that Potrie and Sambarino used. Okay, so they use this thing called Sinai-Royal-Bowen measures. Okay, which is a very strong property of how this kind of contraction rates, when you have a compact flow space, contraction rates, and you reparameterize by the contraction rates, then you can make the topological entropy of the flow 1. Is that kind of result, okay, which we do not have in the non-compact setting. So instead, we have to use a completely different strategy, okay, which is really inspired by some work of Posetti, Sambarino, and Vinhard, who was thinking of these kind of ideas in the case when gamma is a closed surface group. So basically, the strategy is first you show that H rho k equals to delta rho k. Okay, so here you need a geometric finiteness for this. Okay, and this is a counting argument. Okay, you can show that these two things are equal. And then the second step, which is the hardest step, is you show that this delta rho k actually is equal to the Hausdorff dimension of the limit set of your representation. Okay, so there you don't actually need you don't need finite generation there. you just need your representation to have satisfy these things called 1-1-2 hyperconvexity. You require that every wedge product of representation has to be 1-1-2 hyperconvex. Okay, so that's that will allow you to say that the critical exponent, the kth critical exponent, is equal to the Hausdorff dimension of the kth limit set. Okay, and then now you use the fact that your representation is Hitchin, so the limit map is positive. So when your limit map is positive, right, this is something that we sort of see at the end of Francis's talk. It actually tells you that your map is it has a very strong monotonicity property. As you move along your map, the entries of the matrices you use are increasing. Okay, and so then, there's this well-known result that if you have an increasing function from a subset of R to R, then its graph has to have Hausdorff dimension at most 1. Okay, and the same kind of principle you apply here. So the positivity is what tells you that this upper bound gives you the upper bound of the Hausdorff dimension of the limit set. Okay, so that's how you get the upper bound, and then how you get the rigidity, it means how you see that equality holds if and only gamma is a lattice. That's another long story. Okay, but so I won't try to explain that here. Okay, maybe if I have time at the end, but probably not. All right. Okay, any questions about this? So these are the statement of all the theorems that I would like to present today. Okay, so the last part of my talk, I would like to. So one more thing is that especially when Potrie and Sambarino first proved their result, this is seen as surprising. Okay, because if you look at, in the case of a closed surface group, right, if you don't take my kth topological entropy, you use like what we call the Hilbert entropy. So what is this? Is you use the same definition as the topological entropy, except instead of using lambda k over lambda k plus 1, you use lambda 1 over lambda d. In this case, Sambarino proved that this number for any Hitchin representations at most 1, right? In fact, you can make this number get arbitrarily close to 0. Okay, so this is very non-constant. Okay, but then if you take this h rho k, then they're all constant, equals to 1. Okay, so that was sort of surprising when they proved this. Okay. All right, any questions about the statements of the results? Yeah, but only if gamma is not a lattice. So you take gamma to be a convex co-compact free group, then your limit set is some Cantor set, right? So you shouldn't expect that to have Hausdorff dimension 1. Right? But I'm saying, like, as long as your limit set is the entire boundary of H2, then that's the only situation your Hausdorff dimension is 1. Your entropy is 1. That's right. Okay. All right. So the last part of my talk, I would like to sketch the proof of the first theorem that I discussed today. Okay, which I restated here. So if gamma is a geometrically finite function group, then representation rho from gamma to SLDR is data transverse if and only if it's cusped data Anosov. Okay, so one direction is relatively easy. So to show that if you are cusped data Anosov, then you'll be data transverse is relatively easy. Okay, because in both situations, for both cusped data Anosov and data transverse, you have continuous r-equivariant transverse maps. Okay, for cusped data Anosov, you have this contraction property of the bundle, right? And as we saw, one of the first proposition that I showed you tells you that the contraction property of the bundle allows you to say that your ratio of the singular values have to go to infinity. Okay, but once you know the ratio of the singular values go to infinity, then you use the key linear algebra proposition that I discussed last time to show that you have this strongly dynamics preserving property. Okay, so that part is relatively easy. Okay, the hard part really is to go the other way. So if I start with something that's strongly dynamics preserving, a limit map that's strongly dynamics preserving, how do I build a norm, right, for which I have this correct contraction? Okay, so that's the difficulty here. Okay, so let me try to explain how to build this norm. Okay, so first, these kind of the norms that we build here are what we call canonical norms. Okay, so it's a bit of a long construction, but first we pick any alpha in PSL2R. Okay, so I don't even have a group here. I just take any element alpha in PSL2R, and I take its lift into SL2R. That's alpha tilde. Okay, I choose a unipotent lift. Okay. And then the proposition is that, okay, given this, for this choice of alpha, and if you pick any weakly unipotent G in SLDR, okay, so the weakly unipotent, you should think of it as unipotent, except maybe you can apply a compact group. You can left multiply by a compact group, a compact element in the maximal compact of SLDR. Okay, there's a representation C from SL2R to SLDR such that psi of alpha, such a psi of alpha tilde equals to GU, and GSS commutes with every element in psi of SL2R. Okay, so again, remember when for my element to be weakly unipotent, it means that when you write its Jordan-Chevalley decomposition as a product of GU and GSS, the GU part is unipotent and the GSS part lies in a compact. Okay, lies in the maximal compact. Okay, and so this is saying that whenever you have such a G, right, you can find a representation that takes the alpha you chose to this GU, okay, a representation from SL2 to SLDR, and the semi-simple part of your G is going to commute with the image of the entire representation. Okay, so this part is not, I mean, this psi is nothing very mysterious. You can construct it explicitly. Basically, you look at GU, right? GU is going to be some upper triangular unipotent matrix, and you look at its blocks, right? It's the Jordan blocks, and basically for each Jordan block, you put an irreducible SL2R there. Okay, so you can build it. So you kind of think about it. The most obvious thing you do works. Okay. Okay, so I refer to any such psi as a cusp representation associated to this pair alpha in PSL2R and this weakly unipotent element G in SLDR. Okay. Okay, then I say okay, so now I look at this vector bundle over T1H2. So it's T1H2 times RD over T1H2. Then I say that a continuous norm on this vector bundle is compatible with psi if for every vector V in T1H2 and for every Z in RD. So I'm thinking of this Z as sitting in the fiber above V. Okay. This norm is invariant under GSS and is equivariant with respect to psi, right? Meaning that when you have this representation psi, right, this defines for you a PSL2R action on this bundle, right? Just like how whenever we had a representation of gamma, we had a gamma action on this bundle. Now my representation is defined the entire SL2R. So I have an SL2R action on this bundle, okay? And so this is saying that when you apply an element of SL2R on this bundle, so you're hitting the guy in the fiber, right, by C of H, and the guy in the base by just H, right? When you do that, that preserves the norm. Okay. Okay, so this is a definition, and you can show that such norms always exist. Okay, so the reason is because PSL2R acts simply transitively on T1H2. So if you look at the SL2R action on T1H2, right, the stabilizer of any point is plus or minus is negative or plus or minus identity. Okay. And when you look at psi of minus identity, by the property of the GSS commutes with the entire image of the group, you can these two elements commute. Okay, and you can use that to show that this actually has to lie in a compact Lie subgroup of SLDR. Okay, so now how do I build such a norm? I just pick a point and I choose a norm that is invariant under these elements in this this is a compact group, so you can find an inner product that is invariant under this group, and you use that, and then you translate it around the entire T1H2 using the PSL2R action. Okay, so you can build such a norm. Okay, so what's the upshot here, right? Every time you give me a parabolic element alpha and a weakly unipotent element G, I have this particular class of norms on T1H2 times RD, of the bundle T1H2 times RD over T1H2 that I can consider. Okay, with these properties. Okay. All right, but this is about now let's go back to our cast data loss of representation. Okay, so again, gamma is a geometrically finite function group. Okay, so then I'm going to choose parabolic fixed points P1 to Pn in lambda gamma, such that the gamma Pi's and gamma Pj are distinct for I, not J. So the gamma orbits are distinct. And also the union of all the gamma orbits of the Pj's gives you a set of all parabolic fixed points in lambda gamma. Okay, so let me see, I have a picture. So here is really what I'm doing. So here I have two cusps, 1 and 2. Okay, so for each cusp, I'm going to pick I'm going to pick a parabolic fixed point pi that corresponds to this cusp. Okay, and then for 2, I'm going to pick a P2. Okay, and then for each of these each of these parabolic fixed points, I want to choose a hollow disk centered at those points, so that when I project down, I see exactly this. Okay, I can do this because my geometric finite assumption tells me I only have finitely many cusps. So I just need, if you pick finitely, you can pick finitely many points in lambda gamma with this property. Okay. Oh, I haven't picked the cusp yet. Okay, so now I haven't picked the hollow disk. So here, when I choose the hollow disk, I want to choose them. So for each j, right, for each of the pj's, I'm going to pick a hollow disk center at pj, right, so that gamma hj equals, for every gamma in gamma, either gamma has to leave this hj invariant, okay, in which case it has to be something that stabilizes the pj, or has to take hj off of itself. Okay, and this is just saying that this hollow disk that I take, when I project it down into the surface, they actually look like cylinders about the cusp. And these cylinders do not intersect each other. Okay? Okay, then I'm going to let hj denote the intersection between the unit tangent vectors over this hollow disk and u gamma. Okay, so in other words, I'm looking at all the unit vectors in this hollow disk, so that if you look at the forward and backward points, both of them lie in the limit set of gamma. Okay, so that's my UHJ. Okay. And then if I have data transfer representation rho from gamma to SLDR, okay, then for each of these cusps j equals to 1 to n, I'm going to choose a cusp representation, which I denote by psi j, associated to alpha j, rho alpha j, right? So remember, if I'm the theta transverse, I know that whenever I take a parabolic element alpha j, rho alpha j has to be weakly unipotent. Okay, so I can do this. Okay, and then I choose a continuous norm on this bundle EJ, right? Which is T1H2 times RD to T1H2. But now this bundle here has a natural SL2R action given by psi j. Okay, so you should think of this as specifying a norm on the part of the bundle that lies over the cusps. Okay, and you specify in this way, right? Okay, so that's what I just said. So now you take these norms and you restrict it to just above each of these hollow disks. Okay, so if you quotient out, you're specifying a norm over each of these cusps. Okay. Okay, then definition, I say a continuous norm on E rho hat over U hat gamma. This bundle is canonical if its lift to the bundle E rho over U gamma restricts to this norm J, which I just defined, on the entire E rho. Okay, so basically what I'm saying is, for each cusp, okay, so what am I doing here? For each cusp, right, I specify a representation, this cusp representation, and using this cusp representation, I specify a norm, right, on this hollow disk. Okay, and if I pick any norm on the bundle E rho that when I restrict it to the hollow disk agrees with a norm of this form, right, then I say that is a canonical norm. Okay, so I'm specifying what the norm is at the cusp using this cusp representation. Okay. Okay, and then these norms exist again because you can use partitions of unity to do it. I have these norms on the cusp. I pick any continuous norm on the complementary region, which is compact, and I just glue them using partitions of unity. Okay, to get a continuous norm on the entire bundle. Okay, and the proposition you can prove is that if gamma is a geometrically finite function group, and rho from gamma to SLDR is theta transverse, then rho is cos theta not with respect to any canonical norm on E rho to U gamma. Okay, so from this theta transality, so from the strongly dynamics preserving property, right, you can show that your representation has the correct contraction property with respect to this family of canonical norms, these canonical norms. Okay, so actually, I did not say this, but any two such canonical norms that you define are bi-Lipschitz to each other, which is not super surprising because on the cusp you have very good control of what they need to be, right? And the rest of the convex core is compact. Okay. Okay, and so this implies the difficult direction of the theorem, right? Because now I start with a theta transverse representation. I found some canonical norm, some norm, right? where you have where this cusp where you have the correct contraction, so your cusp theta not solved. Okay, and in fact, as a corollary, this tells you that if you start off with a cusp theta and also representation, right, then you must be cusp theta and also with respect to one of these canonical norms. Okay, so this tells you when I say cusp theta and also, in a priori I just say you just need to have the correct contraction property with respect to any norm, but in fact you have to have the contraction property with respect to this particular norm. Okay. Okay, and you can sort of imagine how this is important when you want to prove the stability theorems, right? Because you want to say you perturb your representation a little bit. You need to understand how the norm is changing that you're contracting in respect to. Okay, so this gives you control over that. Okay. Oh, okay. So now maybe I have 10 more minutes. I'm going to maybe sketch the proof of this proposition, right? So when you're theta transverse, how do you show that you are cusp theta and not off? Okay. So the first thing you do is you show that the correct contraction property holds if instead of using the splitting that comes from my representation rho, I use the splitting that comes from my cusp representation psi j. Okay. So meaning you first show that this cusp representation psi j emits continuous psi j equivalent transverse maps eta j from the entire boundary of H2 to F theta. So this is again not super surprising because I told you that the psi j is obtained by taking direct sums of these irreducible SL2Rs, right? And each irreducible SL2R, you have a limit map, you take the direct sums, you can get some kind of limit map as well. Okay, so that's what this eta j is. Okay. And then, so once you have this eta j, you can use that the same way that we did before to construct these vector sub bundles, theta kj and ckj, that splits the bundle ej. Okay. So these are SL2R invariant and flow invariant. Okay, so we have the splitting of this bundle ej. Okay. Okay, and then you show that if you take a continuous norm on ej that's compatible with psi j, then you have the correct contraction property. Okay, this is not super surprising because this is basically an SL2R. Everything here just, there's no, everything here comes from irreducible SL2Rs, okay? And so you basically, the point is if you can show this kind of contraction for the irreducible SL2R, for SL2R, you can use the irreducible SL2R and direct sums to show this kind of contraction property, okay, for the cusp representation, okay? So now what do you have, right? So here I have my cusp, PJ, okay, so this is my hollow ball, okay? And then, over this hollow ball, right? By the definition, the canonical norm that I want to show you have the contraction property with respect to, and the norm that is compatible with psi j, they agree on this hollow disk. Okay, and then above every point inside of the unit vectors in this hollow disk, you have two splittings now. You have a splitting that comes from the limit map of the cusp representation. So this should be eta j, not eta. Okay. The limit map for the cusp representation, and then you have another splitting that comes from the limit map of your anosov representation. And by what we said previously, now we know that if you look at the splitting for eta j, so this green splitting, as you flow, you have the correct contraction property. Okay, so the question now is, why should this splitting that comes from my C have anything to do with the splitting that comes from my cusp representation? Okay. Okay, but that's something that we prove. What we prove is that when you go sufficiently deep into the cusp, right, then the corresponding splittings become closer and closer to each other. Okay, so more formally, okay, what this says is that if gamma in SL2R is a hyperbolic element whose attracting fixed point is Pj, okay, then for any point x in the theta limit set of gamma, when you take x and you apply gamma n to it, and then you evaluate it using C, and you apply psi j of gamma minus n to it, that converges to eta jx. Okay, so here's the picture to describe what I'm saying. So here I have the parabolic fixed point Pj that I'm interested in. Okay, and here, so imagine I have my cusp, my hollow ball, my hollow disk center at Pj, and this is some flow line that passes through the hollow ball, and the endpoints are x and y. Okay. Then you have two limit maps here, right? The first limit map is the limit map that comes from the cusp representation. That's my eta, right? That's the green one that I drew. Okay, so this basically is like the limit maps or the direct sum of limit maps coming from irreducible SL through Rs. Okay, and then you have another limit map that of your theta and also representation. That's my C, which I draw in dark purple here. Okay, and if you look at it like this, your dark purple limit map has nothing to do with the green limit map. Okay, but then what I'm saying is that instead of just applying the dark purple limit map, I take my X, I apply gamma n to it to move it very, very deep into the cusp, to make it very, very close to PJ. And then I apply the limit map C, and then I apply psi j of gamma minus n, right? So if you define psi n to be this map, so you apply gamma n to your point, apply C, and then apply psi j of gamma n minus, then what you get is this pink curve that converges to the green curve as you let n go to infinity. Okay, so this is formally how to say that as you go deeper and deeper into the cusp, right, the limit map of your cusp theta and also representation and the limit map of your cusp representation, right, agrees. Okay, get closer and closer. Okay, and so this tells you that if you take a small enough hollow disk centered at PJ, then the two splittings you get become very, very close. And once you are very, very close, you can show that the contraction property also holds for the splitting that comes from your from C instead of from eta. Okay. Okay, and once you have that, then you're done, right? Because then you've shown that you're not done. You show that the correct contraction property holds on the cusps. Okay, but then now you do that for every cusp, and then you can use a compactness argument to say that if you have any flow line, right, you have this correct contraction. Okay, basically, if you spend too much time in the cusp, then you use the contraction that you prove on the cusp to say that you have the correct contraction. If you don't spend a lot of time in the cusp, so every time you go into the cusp a little bit and you come back out, go into the cusp a little bit and come back out, then you can thicken your convex core a little bit to get a bigger compact set, right, where your flow lines spend a lot of time in. Okay, and then you can get the contraction property there using compactness arguments. Okay. So that's basically the gist of the proof. All right. Okay, so that's all I wanted to say. Thank you.